I want to do some more examples, exercises again to illustrate properties of groups and you, so that you become comfortable with operating with groups. So, let me ask you a new problem. So, here let us say G is a finite group. In this problem I am working with a finite group. Recall that, in other words, remember what are finite groups from my earlier videos. G has only finitely many elements. So, the problem is the following. So, I am giving you an exercise that I will solve in detail. So, G is a finite group. I want to show that for every element of G there exists a positive integer n such that a power n is identity. Okay, so, just a piece of notation, because maybe I have not clearly defined this in the previous videos. When I write a power n will mean a star a star star a n times. Whenever I write a power n, I always mean this, because this is a shortcut. So, star is the operation. Remember, here we are working with an arbitrary finite group, and you will have to get used to thinking like this. It is not Z, it is not Q, it is not it is not S3, it is not the roots of unity. So, it is not any specific thing, it is any group, and the problem should not use any specific properties of examples of groups. It must only use properties that all groups have. So, here G is a finite group and star, let us say, is the operation. It is a shortcut, it is an easy notation. Instead of writing a star a star a star a always n times, we will simply write a power n. So, that is what I mean. So, now let us come back to the problem. It is asking you, show that for any element a of G there exists a positive integer n such that when you apply a to itself n times, you get the identity element. Also remember, E is the identity element. That is my standard notation. For a group, E will stand for identity element. Generally, when I am working with a general group, E will stand for the identity element. So, what is the solution to this? So, G is a finite group. So, we will have to use that. So, let us do the following. So, I am going to consider the elements E, A squared, A cubed, A power 4, A power 5, like that. I can take A power 100, A power 101 and so on. So, what am I doing this here? So, I am starting with identity, that is you can think of identity as A power 0 always, that is again notation. A power 1, that means just A squared means A star A, then A star A star A, A star A star A star A star 5 times, 100 times, 101 times. Now, these are all elements are, where are these living? All these are elements of G. Why is that? Because, why is this? Because G is closed. I will write G is a group. Star is a binary operation on G, right. So, A is in G, remember A is in G, that is the starting point. A is in G, so A squared is in G, A cubed is in G, A to the 4th is in G, A to the 5th is in G, A to the 100 is in G, A to the 101 is in G, and so on. So, these are all elements of G, but remember that G is a finite group. We are going to use this very important hypothesis. G is a finite group, and here we have seemingly infinitely many elements, right, because you have A squared, A cubed, A power 4. You can keep doing this, you can do A power 1000, A power 10,000, A power 1 lakh and so on. But how do you justify this? Now, G is a finite group and these are all elements in that finite group, and they are seemingly infinite, but they cannot be infinite. So, what is the implication here? So, for some positive integer n and m, we must have right. Is it clear? Because if these numbers, these elements a squared, a cubed are all different, that will be an infinite set contained inside G, which is a finite set, which is impossible, which is an absurd statement. So, this cannot be an infinite set, which means there must be repetitions. If this is not infinite set, then some two elements, in fact, many of them will collapse. So, I am just saying that for some positive integers n and m, and of course, I have to insist that n is not equal to m, otherwise a power n is certainly equal to a power m. So, for some positive integers n and m which are different, we must have this. Again, if not, if this does not happen, then a power n is different for each n, and this set a power n, the set consisting of all powers of a, is an infinite set living inside a finite set, giving you a contradiction. So, a power n is equal to a power m for two different positive integers. Because n is not equal to m, we can assume without loss of generality that n is strictly more than m. We can assume that, because one of them is bigger than the other, we will simply say n is bigger than m. Then let us now play with group properties. So, we have a power n equals a power m. So, let us multiply this with a power minus m. Okay. Now, again what is a power minus m? If you are confused about this, I will make a remark here. What is a power minus m? It is just a shorthand for, you take a power minus m is by definition you take the inverse of a and write it like this. Okay. So, it is convenient to write this element as a power minus m. So, this is just notation. So, this is notation. Instead of writing a power minus 1 power m always. So, here what we are really doing is, so let me just, because I am doing this for the first time, I will just for clarity multiply both sides . So, in other words, I have a power n, a power m, I get a power n but now let us see what happens. So, this is, now let us recall what is the definition of a power n. So, this is n times and a power minus 1. So, this is really again star, in general the operation is star. So, a power minus 1 star a power minus 1 m times. So, that is the left hand side. On the right hand side we have a power m, which is a times a m times star a inverse also m times, right. So, this is just expanding these terms. So, but this is, you can cancel this. What is the right hand side now? You have a times a inverse, which is identity. So, that will cancel, the previous one will cancel with this, and finally, this will cancel, because this is exactly the same number. This is m, this is also m, this is e, this is e, and here, but we are assuming, remember, n is strictly more than m. So, we can't cancel all of them. So, we can cancel m of them. So, cancel m of them, what will be left on the left hand side? We cancel m copies of a on the left hand side. Using a inverse. So, then what will be left with is a power a star a. So, this is the left hand side is e, right hand side is, after cancelling m copies of a from here, how many will be left with? we will be left with n minus 1 m copies. Okay. So, that means a power n minus m is E. Okay. Let us go back and see what the problem asked us to do. Problem asked us to do, given an arbitrary element of the group, there exists a positive integer n such that a power n is E. Did we get that? Yes, we got that, because n minus m is a positive integer, which is a positive integer by the assumption that n is strictly more than m, and we did get a positive integer such that a power that is E. So, we have solved the problem. So, I hope this calculation here is clear to you. Maybe just a quick calculation. I mean, if you, in case you are confused about this, I just want to do it with specific numbers. So, let us say n is 3 and m is 2, just n is 5 and m is 3, let us say in the previous example. So, that means a power 5 is equal to a power 3. I am multiplying with, if you go back and see, I am multiplying with a power minus 1 whole power the smaller one, which is m. So, here I get a power 5 times a power minus 1 power 3 is equal to a power 3 a power minus 1 power 3. So, that means I have a product of a 5 times, I will cancel 3 of those. So, I get a squared and here I get E. So, this is just specific example, so that you understand this. So, we have solved a problem. We have solved the problem which asked in a finite set this happens. Remember that we have crucially used the finiteness hypothesis, because we want to say that this set is not finite, because it sits inside a finite group, it is not finite, and hence there must be repetitions. So, it must happen like this. Okay. And if you can see, this is not going to be true, this is not true if G is not finite. For example, we take, let us say Z is Z, and we take the element 1 in G. So, Z is under addition. Okay. So, I should mention this, because Z is just a set. We, in order to make it a group, we will take the addition. If you take 1 in G, remember the notation that I have been using is a power n, that is just a star a n times. Here the operation is addition. So, it is a bit confusing to think of that power notation in terms of addition. Here spelling out exactly, does there exist a positive integer n such that 1 plus 1 plus 1 is the identity. Remember, a power n is E. So, that means we want a star a n times. Does there exist something like this? So, 1 plus 1 plus 1, because addition is the operation here and the identity element is 0. Does there exist something like this? Certainly not, because this is because 1 plus 1 plus 1 n times is actually n, but n can't be 0. You are asking for n to be positive. So, n can't be 0. So, it is not true if G is not finite. This property is very specific to finite groups. So, just I will end this video with one more example which is very similar to this. So, a different problem now. Let us say G is a finite group again as before. Show that there exists a positive integer n such that a power n is E for all. Okay, so, if you read the problem carefully, let G be a finite group, show that there exists a positive integer n such that a power n is E for all a in G. What is the difference between this and the previous problem? Here I am asking you, show that for a given element A, there exists a positive integer n such that a power n equal to a. So, this n has to be chosen after I get a. So, it can depend on a. In the new problem, I am asking for an n which works for every element of G. So, n in particular should not depend on a, but this is now easy given that we have already solved the previous problem. So, solution by the previous problem for any a in G, there exists a positive integer. Let me now call it n sub a because this positive integer from the previous problem depends on a. So, let us call it n sub a such that a power n sub a is 1 or rather e. Okay. Remember, this is the content of the previous problem. There is a positive integer n a such that a power n a is e. Now, we have one such positive integer for every element of a, every element a of G, but again let us use the fact that G is a finite group. So, we have n a for every small a in G. So, now I simply define n to be maximum or rather let us say product n a in G. So, this is like if G is a 1 up to a r, G is a finite group, right. So, I am defining it to be n a 1, n a 2, n a r. So, I am for every element of the group there is an associated positive integer. I am taking the product of those positive integers. Now, I claim that this n will have the required property. We claim that this n works. In other words, that is a power n is e for all n G. Why? Why is this true? This is clear if you think about this for a minute. So, n remember is n a 1 n a r, right. So, now if you take a power n, one of the a's is equal to a is equal to one of the n i's. So, a power n is a power n a 1 n a r, okay. But let us say a 1 equals a just for simplicity. Okay. So, actually let me do a 1 power n. So, I have a 1 power this, right, because n is equal to this. But if you now think about this, it is what is this? This is a 1 star a 1 star a 1. How many times? It is n a 1 n a 2 n a r times. Okay. So, you can now combine this in n a 1 times, okay, and then combine this again in n a 1 times like that. So, what I am saying is, so because this number is divisible by n a 1, I can break up this huge product into smaller products, each one consisting of n a 1 times. But remember, a 1 power n a 1 is identity, that is how n a 1 was chosen. So, this is identity, this is identity, this is identity. So, the content of all this is that you can use the usual exponential rules. That means, this can be written as a times n a 1 power n a 2 n a r. Okay. Usual exponential rules that you have learned in school say that this is equal to a 1 power the product of these two, but a 1 power n a 1 is E and E power anything E is E. So, this is the shortcut of the proof. Okay. But the proof of this is this, because I am using the exponential rule as a exponents as a notation, I can't use exponential rules that I have from integers and real numbers and rational numbers. I have to justify that, which this does. So, maybe I will leave this as an exercise for you. If a power n is identity and n divides m, then a power m is also identity. So, this is an exercise which I have essentially done here, but maybe not in great detail. So, I would like you to all I would like all of you to do this carefully. If a power n is identity and n divides m, a power m is also identity. So, now given this exercise, if you accept this, the problem is solved. So, we did get a positive integer globally independent of elements of A such that a power n is identity. So, this I will end this video with this, and in the next video I will do one more problem in a lot of detail, and then we will continue our study of groups.